What specific problem does your method of instruction back and forth translation aim to solve in the context of language model fine-tuning?
The method of instruction back and forth translation aims to address the limitations of existing instruction tuning data generation methods, particularly the reliance on high-quality text sources like ClueWeb, which is costly and restricted. By utilizing an open-source corpus like Dolma, our approach generates instruction response pairs through back translation and response rewriting, enhancing accessibility and scalability. This method improves the quality of instruction tuning data by incorporating diverse information from the web, while ensuring that the responses are refined through an aligned LLM, thus avoiding overfitting to a single model's knowledge. Our findings indicate that this approach yields better performance compared to traditional distillation methods, as it effectively combines the benefits of diverse web-sourced data with high-quality model annotations. Overall, the back-and-forth translation method seeks to enrich instruction tuning datasets, ultimately closing the performance gap between open and closed large language models.
How does the proposed instruction back translation method work? Please illustrate the process step by step, including how the forward and backward models interact with the data.
The proposed instruction back translation method operates through a systematic pipeline involving several key steps. First, a base language model is fine-tuned on a set of seed instruction response pairs to create a backward model, denoted as M_YX, which learns to generate instructions from responses. Next, candidate responses are extracted from a web corpus, such as Dolma, and paired with the generated instructions to form candidate instruction response pairs, hat X_I, Y_I. These pairs are then scored by a forward model, M_XY, which is also fine-tuned on the same seed data to evaluate their alignment on a 5-point scale. Finally, only the highest scoring pairs, score 5, are retained to construct the final instruction tuning dataset, ensuring that the data is both relevant and high quality. This process effectively combines the strengths of both models to enhance the quality and diversity of the instruction response pairs generated.
Can you provide a specific example of how the rewriting process improves an initial web-crawled response from the Dolma corpus based on the generated instructions? Walk through the example to clarify the changes made during rewriting.
In the rewriting process, an initial web-crawled response from the Dolma corpus is improved by conditioning it on a back-translated instruction. For instance, if the initial response is a raw text segment that lacks clarity or structure, the Llama 2-70B chat model is prompted to rewrite it based on the corresponding instruction. This process enhances the response by improving its coherence, organization, and overall quality, making it more suitable for an AI assistant's output. The rewritten response is then expected to better align with the instruction, resulting in a more informative and user-friendly answer. The paper indicates that this rewriting step is more effective than filtering alone, as it significantly enhances the quality of the instruction tuning data by incorporating diverse information from the original web text.
What theoretical or practical advantages does your approach of using back-and-forth translation provide when compared to existing methods like distillation or ClueWeb parsing?
Our approach of using back-and-forth translation offers several theoretical and practical advantages over existing methods like distillation and ClueWeb parsing. Firstly, by utilizing an open-source corpus like Dolma, we eliminate the data access restrictions and pre-processing complexities associated with ClueWeb, which requires paid access and specific HTML parsing rules. Secondly, the rewriting process enhances the quality of responses by leveraging the diversity of information found in web-sourced texts, resulting in instruction response pairs that outperform those generated through distillation alone. Specifically, our method yields a 6% improvement in win rate over ClueWeb-based datasets, demonstrating its effectiveness. Additionally, our pipeline generates a larger dataset of 51.2K instruction response pairs, significantly more than previous methods, while maintaining high quality through aligned LLMs in the loop. Overall, back-and-forth translation not only improves data quality, but also enhances scalability and accessibility in instruction tuning data generation.
How did you validate the effectiveness of your proposed method? Describe the experimental setup, datasets used, and the metrics for assessing performance improvements.
To validate the effectiveness of our proposed method, we fine-tuned the Llama 2 models on instruction response pairs generated from our back and forth translation pipeline and compared their performance against various baseline datasets. We utilized the common crawl subset of the DOLMA corpus for initial web-crawled responses and employed 3,200 high-quality seed examples from the Open Assistant dataset for training the forward and backward models. The performance was assessed using the AlpacaVal benchmark, where we prompted the fine-tuned models to respond to 805 questions and reported the win rate over the Text DaVinci 003 model evaluated by GPT-4. Our results indicated that fine-tuning on our rewritten responses significantly improved the win rate by 3.6% compared to previous back translation data and outperformed other existing distillation datasets. This comprehensive evaluation demonstrated that our method not only generated a larger dataset of 51.2K instruction response pairs, but also enhanced the quality of the responses through the rewriting process.
What were the key results obtained from using your method on the AlpacaVal benchmark, and how do they compare to results achieved with other data generation approaches?
The key results obtained from using our back-and-forth translation method on the AlpacaVal benchmark showed a 3.6% improvement in win rate when fine-tuning the Llama 2-70B model on our instruction response pairs compared to using back translation data from previous work. Additionally, our method outperformed other existing distillation datasets, such as Shared GPT, Alpaca GPT-4, and Self-Instruct, by at least 3.2%. Specifically, fine-tuning on rewritten responses from unfiltered instruction response pairs yielded better performance than fine-tuning on filtered responses that had not undergone rewriting. Overall, our approach generated 51.2K instruction response pairs, demonstrating that the combination of instruction back translation and response rewriting significantly enhances the quality and effectiveness of instruction tuning data compared to traditional methods reliant on distillation.